Hi, this is Sam Ziss from Dr. Uselin's Thermodynamics class. I'm going to be working through my original problem for Chapter 5 today. I'll start by reading the problem statement. It says refrigerant 134A is heated by water flowing through a condenser as shown in the diagram below. If the heat transfer rate is 22 kilowatts, calculate the mass flow rates for both the water and the refrigerant. So in red here I have written our goals. We eventually want to find the mass flow rate for the water and for the refrigerant. So what we're seeing in this condenser here is I'm starting with this blue pipe passing through the back. We have the water flowing initially at a temperature of 10 degrees Celsius and at a pressure of 320 kilopascals. It leaves the condenser at a temperature of 20 degrees Celsius at that same pressure. Meanwhile, flowing through the black pipe, we have the refrigerant 134A at a starting temperature of 70 degrees Celsius and a starting pressure of 1200 kilopascals. It passes through the pipe and has been cooled to a temperature of 30 degrees Celsius at that same pressure. So what we're seeing is that the water has been heated by the refrigerant, causing the water to raise to a higher temperature and the refrigerant to lower to a lower temperature. The first thing that I did was I went to my tables for those initial conditions and found some enthalpy values. So starting with state 1, from those given temperature and pressure values, we decided that water was compressed, it was not superheated, and I found an enthalpy of 42.022 kilojoules per kilogram, and that came from table A4. Similarly, for state 2 in green, we found that H2 has a value of 83.915 kilojoules per kilogram, again from table 4. Moving to the refrigerant, we find that those given values for temperature and pressure give us that the refrigerant at the starting value was superheated. So I started at table A11 to find that out, and from table A13 I found that H3 was 300.61 kilojoules per kilogram. Moving to state 4, when the refrigerant left the condenser, we find that it's back to being compressed. So using table A11, we find that H4 is 93.58 kilojoules per kilogram. And the reason that I went and found these values is that they're going to be useful when we look at our energy balance equations below. So one very important fact for heat exchangers is that for our example here, the water lost heat the water gained heat from the refrigerant. So any heat gained by the water will be equivalent to any heat lost by the refrigerant, and this value was just given to us as 22 kilowatts. And we're going to use that when we go ahead and look at our energy balance equations. So I started with this equation for water. Again, the energy rate in will be equal to the energy rate out. I threw out the work rate values, no work is being done here. And I threw out Q dot W out because the water is not losing any heat. So plugging in here, we had that Q dot in was 22 kilowatts. I wrote it as kilojoules per second. And we have that M dot W times H1 added to that value for Q dot W in will be equal to M dot W times H2. Calculating this, we get our desired value of the mass flow rate for the water being 0.525 kilograms per second. Similarly, we will write an energy balance equation for the refrigerant. Again, no work is being done, so we throw out the W dot values. The big difference here is that, kind of contrary to the water, the refrigerant is losing heat, so Q dot R in will be 0. It's not gaining anything, it is only losing heat, which is that value that was given to us as 22 kilojoules per second. Then plugging in our H3 value of 300.61 and our H4 value of 93.58 kilojoules per kilogram and doing a little bit of algebra, we get our final value for the mass flow rate of the refrigerant as 0.106 kilograms per second. Thank you very much for watching.